Good evening. My name is Eduardo Lacerda Campos, and I'm going to present scientific research developed by the Potiguar rocket design called rocket recovery using 6 degrees of freedom simulation. So, in recent years, we have been watching a remarkable achievement of our first rocket booster vertical landing. An example is the rocket Falcon 9 developed by the company SpaceX. This achievement has been celebrated as a huge step towards space exploration, which finally can unleash our space access to the space. However, the great challenge to developing rockets like that has been the development of knowledge to measure its altitude, angular velocity, position, velocity, and at the same time, control its descent movement. Thus, the Potiguar rocket design studied a control strategy which enabled a rocket to reach a desired land place. To assess that control strategy, the team has previously developed the all 6 degrees of freedom rocket simulator, which enables to create a three-dimensional environment. So the background. So first, as I explained, the team has developed that software which enables to simulate the rocket flights and can simulate different situations as loose on things, different parachutes, can simulate many other different situations. And that was the first article we have published about that topic. Thus, once we have our own simulator, the next step was to study how to control the rocket descent movement. But first, I'm going to explain a little bit about the background theory involved in the simulator. First, to define our equation, it's necessary to define the reference frame. For this working, the Earth-centered inertia was selected at the initial frame, and it means that the frame is placed at the center of the Earth, and it does not rotate with the planets. Then we have the reference frame at the rocket. It has been placed at the center of the mass, where the x-axis points toward the nose, y-axis points toward the pitch rotation, and the x-y points toward the yaw rotation. So now to represent our variables within each of the frames, this study using a layer above each variable, as you can see in this formula here. An example have here the letter B to represent the variable expressed in the rocket frame, and the letter I to represent when the variable is represented in the frame, in the Earth reference frame. Then the rocket model is presented by the following differential equations. To represent its attitude, the quaternion is chosen, which has some advantages, like it does not possess singularities and present a compact representation. Furthermore, to simplify the model, the Earth was considered as a sphere, and the rocket has a parachute to reduce and keep a steady descent velocity. On the set of differential equation, it's necessary to find the force, I am pointing here, and the torques, I am pointing here in the slide, which are applied on the rocks. So, about the forces. The force applied on the rock were calculated by finding the aerodynamic drag generated by nose, body, fins, parachute, and the controller thrust, as you can see in the picture. So, about the torques, each of the forces applied on the rock can generate a torque, which can be calculated by the following equation. Finally, a damper effect was included to simulate the drag force created by the angular velocity. This drag force is necessary to avoid the rock oscillate like a mass spring undamped system. I'm going to talk a little about the control we have assessed on this study. When you think about the traditional control law, we have to know the desirable path which the rock must follow. Within this approach, the error is calculated by finding the difference between the actual and desired position in space. But once the rock has already taken a wrong path due to external disturbance, to get back to the desired path demands energy. Instead of expending energy to get back into the original path, the idea was to investigate a strategy which calculates the error between the desired land place and the predicted land place. So, thus, the algorithm to do that is described by the following script, where first, we decomposing the rock velocity which goes towards the ground and parallel to the ground. Then, we using the rock velocity towards the ground to find the time to reach the Earth's surface. So, by using the velocity and that time, we can predict where the rock are going to arrive. So, once you have the predicted land place and the desired land place, you can calculate the error between these two variables. Finally, once you have the error between these variables, you can find the necessary force using just a proportional control to apply a thrust on the rocket to correct its flight. So now I'm going to show a simulation which was carried out by us. So first, we set up the following parameters on the simulator, where the initial velocity is 0. We include a wind effect as an external disturbance. The Earth mean radius is defined. The rock is placed 500 meters above the ground. The desired land place is set on the ground, but there is a displacement on the X and Z axis. So they are going to reach not in the 0, 0, 0 coordinate, but with a displacement. The initial angular velocity is 0, and we set a random initial altitude at the space. So to better assess the control, we running the simulate twice. One, the control is active, and the another is the flight without the control. As you can see, the red line are working with the controller, and it's reached a desirable place in the ground. And the flight without the controller drift a little bit from the desirable place. Of course, due to the wind. So, as a conclusion now, just a simple proportional control strategy used to correct the rocket flight was enough to correct it. And instead of using a fixed path and keeping changing the path, but all the time we predict where the rockets are going to reach and use that information as a signal to the control, shows to us to be a good strategy. We are going to keep studying in another events. So for future works, now we are going to improve our simulator, include more aerodynamic forces, and because when you do that, we can use the rocket body, the fins, and another component to create the forces and torque that are necessary to correct the path. So that's all for my presentation. Thanks for all.
Tim, congratulations for your presentation. It's an amazing work. Very hard field, very innovative field, and we are now open for questions and answers.
I have some. What do you think was the most challenging topic you have faced during the design?
Yeah, now for us was to create that simulator because we decided to do from scratch. Because CoBRUF decided to include one challenge in the competition where we should assess the flight without some things like in the middle of the flight, the rocket lose one things, change some parameter. You should evaluate where the rocket are going to reach. So now we decided to recreate everything from scratch, from the zero. But there's a great advantage on doing that because now you can create many other simulations that is not possible with the commercial, not commercial, but the software that are open to use for the universities or any other situation. So now is to recreate that simulator from scratch. I think these are the great challenge now.
Got it. I think it's a new theme of study. So it is really difficult to find resources for your studies, and I imagine it's really difficult to do this kind of work, and you have done a great work. I'd like very much the way you have treated the problem. I like the way you have presented it in this presentation. Congratulations to the team. It was a really good work.
Mm-hmm.
I also would like to know, in your opinion, what are the main steps actually, what kind of hardware could be integrated to the simulation?
Yeah, you're not now worried about the hardware, because first we should know all the math, all the problems we are going to face, because I have experience on translate something from the simulator to a hardware. It's so easy. When you develop your simulator, you can do many tries that you want. An example, to launch a rocket is a little bit expensive, hard, and you can do it many times as you want to create many different simulations. Like I want to learn to launch one rocket for each week. It's impossible. Nobody has, as a student, has so much money. So we take a different path. Instead of worry about the hardware now, first we are going to develop, understand the math, the strategy. We are going to create an environment in the simulator. You can launch thousands of rockets and try different situations and study it better. The next step now, I'm going to launch a rocket and compare the result with the simulator, where I can improve our simulator. And then when you get more mature, you can thinking about the hardware, because let's say you are now taking baby steps to recreate that simulator.
I would like to make another question in the same line. So yes, you're now in a very beginning of your simulation and your modeling, but every modeling we need to think about how to validate it, right?
Yep.
And I saw that you are thinking about launching rockets to validate your simulation, right? So could you explain more about how would be that process?
Yeah, like now, the CoBRUF, we are going to launch a rocket, and we are going to collect the data. So we have the position, the velocity. You can compare the results with the simulator, just something like that. Because with the simulator, we have all variables like position, velocity, the rotation, the space, the attitude, how the rocket and the position, the rocket in the space. You just want to compare. Now, next week, you're going to launch a rocket. So after that, we are going to pick up the data and compare the results.
So if I understand correctly, your design, you are planning to implement some control in your trajectory. Is that correct?
In the future, not now, because to do that, we need more studies. However, nowadays, there isn't any surface we can use to control its trajectory. It's just a ballistic, specific flight. But it's a step towards create that kind of rock where I can control the flight.
Okay, so right now the goal is to see if your trajectory, the real trajectory, is the same as the 6DOF.
What I can say.
Is that it?
What I can say, I have already compared with another simulator like OpenRocket and others. The result is so close, but I would like to compare and see if I reach a flight with a better precision than an OpenRocket example.
That's great. And about the control, the future work, did you consider other controls besides proportional? What were your analysis to do this modeling?
Not now, because unfortunately we are focused just on create a better simulator. We need time in the future to study more, read more articles. But for example, I read an article where the guys use a paraglide to control its movement. So for now, we are going to study better and try to evaluate another strategies. But in the near future, the focus are going to be to create a better simulator, and then we are going to focus on the control strategy, because there is a huge, say, there are many things to study to understand better how to predict the flight very well. So, we don't want to how to say, do a step more that we can do now. Give a huge step that you can do now.
Yes, yes, that's great. That's very responsible.
Yeah.
And yeah, and but if you were to think about a timeline where if you're looking to the future, where you will be implementing this in tests, even ground tests, what will be this timeline? Which year do you think? Using the evolution you have right now, the instruments and the know-how you have right now, do you see yourself in 1 or 2 years thinking about a test of on this proportional control system?
Yep. I think now the next step, I'm going to create the hardware to measure the variables, because if it's what I imagine. And the next flight, let's imagine the next competition next year. Probably I would like to send instruments to measure its attitude to validate with the model, because say it's more safely than we want to control its attitude at the first flight. They're going to be impossible, something that's dangerous. You should learn in small steps. Maybe if we can change like I say, the parachute, and instead use just a simple parachute, use a glider, maybe in 2 years we can change it. I heard about another participants. They are using different rockets more engine. So it's nowadays we are using just let's say the traditional engine is a little bit hard to control the thrust. Maybe I think I would say now probably next step we're going to use a different parachute, maybe 2 years, something like that.
Great. Those are all my questions. I just want to congratulate you because it's a very grounded project, very responsible project, and you are facing the challenge. And it's a really, really, really hard challenge. And we have now very few players in the world that are facing the same challenge. So
Yep.
you have a plan. You know your limits, and you know what you have now and where you want to go. So this is really, really good. So congratulations.
Yeah, I think with that simulator, you can start to simulate different situations, because if you think just in building a rocket and try to learn by building, it's a little bit hard, because a rocket is expensive, take a long time to build. Launch is a very hard. You can't launch a rocket anytime you want. So our approach is to develop a simulator where everyone in the team can learn by try different situations, different ideas. Like you can try use a paraglider. You can decide to control the motor thrust, like the SpaceX doing now. But of course, there is a long time, much research to do, and take a long time. How do you say? We need time, a long time to develop that technology.
What other in your presentation we have seen your studies about control. What other areas of the rocket design do you think it will need to be studied and developed in order to start precision landing tests in the future?
What I can say, because when you were talking about small rockets, and it's doing by universities, I think it's a little bit hard to create the entire engine, right? When you use a liquid fuel. So maybe for the university competition, are going to be more feasible use a paraglide as example for the small rockets. But once you have teams that reach another level, like 3 kilometers in space, maybe you have another kind of structure and a different engine. They can try to do something different. But it's difficult to guess, to predict what should be the next step. What I can say is about maybe going to be easier using a strategy like a paraglide, where you control the direction, use the wind to guide your rocket. It's going to be easier, feasible for students. Easier, I'd say, easier when you compare as a landing vertically like SpaceX are doing. But there is many interesting things to learn, and it's a challenge just thinking control the paraglider. I think it could be the next step.
Very good. We are trying to stimulate the teams to think about the future, to think about the next steps. That's why I have asked this question to you, and I really liked your answer.
But I heard that there is a competition in the United States where the students create just a kinset, and it is launched by a drone, and you should control the direction using paraglide. I think it's an interesting idea. I have read, found an article just about that, how to control a paraglide, and I think it's probably the next step, because control the thrust is another step of technology. It's not easier to do, demands a lot of time and money. And there's sometimes hard for some university to be found with the money necessary to build rockets like that. So I think it could start for that.
Yes, thank you for your answer and your opinion. Before I finish, would you like to say a few words?
Just thanks for the COBRUF for the opportunity to present this work, for the team, Potiguar rocked, that the opportunity to develop that technology, work together, and the Professor Marinho from the Universidade Federal do Rio Grande do Norte, who supports the team and promotes the idea at the university. And for everyone who are watching and hoping for the new technology and things that we are going to do.
Thank you. Good luck on the competition, and see you there.
Okay, see you.